All right, so here we have an equation to solve, and it is an exponential equation. It's exponential because the variable is in the exponent. So how are we going to solve this? Well, the trick here is to use logarithms. We know many properties of logarithms. If you're not familiar with these, watch my previous videos. But one of the properties we learned about was the inverse properties. And there are two of them. And this describes how logarithms behave relative to exponential functions. And it's the second one we're going to be interested in here. Notice that if I have an exponential function and I apply a logarithm with the same base, notice these have to be the same, then something very nice happens. Whatever the exponent was simply comes out. In other words, another way to think about this is that the logarithm and the exponential function cancel off. Now, it's very important that the bases match, but this is the property that we're going to want to use here. All right, well, before we can use that property, note we have to get the expression that we want to apply the logarithm to in this form. All right, so we're going to want to get it just looking like a to the x. Right now we have a to the x, a is e, but we also have some other crud over here. We got a 4 and a minus 3. So let's take care of that. Let's get rid of those so that we can apply this inverse property. So first what I'm going to do is add 3 to both sides. All right, so that gives me the new equation 4e to the x equals 8. And now let's get rid of the 4. So I'll divide both sides by 4, and that gives me e to the x equals 2. Well, now we're in a situation where we can go ahead and apply this because we have something of the form a to the x. We have e to the x. So what I'm going to apply here is log base e. Now we have another name for log base e, that's the natural logarithm. So what I'm going to do is I'm going to apply the natural logarithm to both sides. Now what the inverse property says is that the natural log and the e cancel off and they bring the x down. And we have solved this exponential equation. Okay, here we have another exponential equation. Let's apply the same technique to try to solve this one. So I'll do the same thing we did in the last one. I'm going to subtract 7 from both sides. Now I'm going to divide both sides by 2. Now I'll apply the natural logarithm to both sides. Natural log again because that's log base e. That matches the base that we have here. Now if you're astute, if you're paying attention, you should notice we're running into problems already. But let's go ahead and keep going. In fact, you could have seen we had problems right here. This is already a huge red flag. But let's keep going. We know that the inverse property says the natural log and the exponential function cancel out. And so I might be tempted to write my solution as this. But those keen observers would have noticed that this cannot be, right? We can never take the log of a negative number. Negative numbers aren't in the domain of the logarithm. Logs are only defined on positive numbers. So this is no solution at all. The answer is no solution. In our next exponential equation, and again it's exponential because the expressions involving x are in the exponent, we have two different bases. So this leads us to a question. Which logarithm should we use? Should we use log base 4 or log base 3? Well, it turns out it doesn't matter. You can actually get away in all of these problems with using log of any base. That will still work. How does that work? Well, there was another property of logarithms which we didn't look at in this video, and it was this one, the power property. Notice the power property, the base of the logarithm does not need to match the base of the exponential function. What will happen when you apply the logarithm is that the exponent on that exponential function will come out front of the logarithm. It's not quite as nice as this property because instead of just being left with whatever the exponent was, we're left with what the exponent was multiplied by this other stuff. So we're going to get some residue left over here, but it's still going to work. It's still going to get the job done. So what this means is that we can use whatever logarithm we want to solve these problems if we're willing to allow this extra stuff to come along for the ride. So one nice logarithm to use is whatever logarithm is on your calculator, and your calculator has two of them. It's log base 10 and natural log. Since we used natural log on the last two problems, I'm going to use log base 10 here. So what I'm going to do is I'm going to apply log base 10 to both sides. Remember, for log base 10, we don't write the 10 base. It's implied. Now we're going to use that power property of logarithms. What it says is that the power comes out front of the logarithm. So we're going to go ahead and apply that. So the power here in this case is 5x minus 3, so it's going to come in front of the logarithm. The parentheses there are important. And again, the exponent here is 2x plus 7, so it's going to come in front of the logarithm. And now we can attempt to solve for x. Notice the x is now out of the exponent, and that's fantastic. So what I'm going to do is distribute the logarithm across. So 5 log 4x minus 3 log 4 is equal to 2 log 3 times x plus 7 log 3. Now let's collect the x's on the left and the logs on the right. So I will subtract 2 log 3x from both sides. And I will add 3 log 4 to both sides. All right, well now we're at a point where we can factor out the x's. We have two terms. They are like terms. They have the same variable part, so we can combine them by factoring out the x. And finally, we can divide by this number on both sides. And this is our final answer. Not the prettiest answer in the world, but it is an exact answer, and so this is how we report it.